instances at any point of time. And we have learned a few things along the way. And this presentation is our effort to share some of our learnings. So as you deploy and manage MongoDB on various public clouds, hopefully this will help you out. So before we get started, can we do a quick show of hands and how many people are actually using MongoDB in production? One. And AWS, Azure. Okay, interesting. All right. So what we do is we'll start with some MongoDB basics. So typically in MongoDB you have three configurations you can deploy. The standalone model, the replica set model, and the sharding model. And standalone model is fairly obvious, it's just a single instance. And it's great for dev and test. You can just bring up a single instance, do your testing, validate your application. But typically you don't want to deploy that in production. It seems a fairly obvious thing to say, but you'd be surprised at how many people are just running a standalone instance in production. And by far, the most common configuration we see is the replica set configuration. And typically that has a primary and some secondaries. So it could be one secondary or it could be two secondaries. And all the writes are typically going to the primary. And the secondaries are replicating from the primary. So this is a typical standard configuration. And in this configuration, you can scale your reads by adding more secondaries, but you cannot scale your writes. In that, essentially all the writes are going to the primary. So if you need to take more writes, essentially you need to increase the size of your application. So this is a fairly simple standard configuration. And the third configuration that is fairly unique to MongoDB or unique to NoSQL databases is a sharding configuration. And this is essentially the scale-out configuration where you can essentially scale out your reads and writes linearly by just adding more shards. And each shard is typically a replica set by itself. And there is a stateless router configuration. Now all the applications connect to the stateless routers, and the routers connect to the backend shards. So as your application workload increases, you can just keep adding more shards, and your reads and writes will increase linearly. Of course, subject to your schema and configuration as well. So basically, this is kind of the money shot for MongoDB, right? This is the reason they exist. Because originally when they started out, it was very difficult to scale traditional relational databases. Because this was the second model, with the primary and the secondary was the only one that was supported. And MongoDB came out with this model to make it really easy. And essentially that was the reason people adopted them. Let's start with the basics. So when you're going to go into production, the first thing you need is to make sure that you have high availability for your databases. And it's a fairly simple setup in MongoDB. You can set up the replica set, you can do a 2+1 or a 3-node replica set. And whether you need a 2+1 or 3 depends on your availability requirements. If you just go with a 2+1 replica set and one of the nodes has a failure, then essentially you are running with just one node, right? If you don't want that situation, you can deploy a 3-node replica set. And then even if you have failure on one node, you still have 2 copies running fine. Okay. And ideally, you want to distribute these replicas across different AZs. And if you're not familiar, AZ is basically a construct introduced by Amazon. It's called an availability zone. And essentially what they're saying is, between the availability zones, there is no shared hardware. There's no shared routers, there's no shared power switches. So the loss of one AC will typically not impact that AC. It doesn't always hold that way, but the majority of the time, it works fairly well. So if you want to deploy a highly available replica set in AWS, you can basically essentially put one replica in each AC. And that will get you like 99% of it. And Azure is similar. Azure when it started out, they didn't have the concept of availability zones. They essentially had something called availability sets. And essentially what it does is it distributes your replicas across fault zones and upgrade zones. So it's similar to AZs, but it doesn't have such strong guarantees in that it doesn't guarantee that there's no shared power source between them and things like that. But recently, they've also started adding availability zones. But it's still a little spotty in that some data centers have availability zones, some of the older ones don't. So for now, I think if you're doing high availability in Azure, you want to do both availability sets and, if possible, availability zones. And if you have any questions, feel free to just stop me. We have a small audience, so we can make this more of an informal discussion. So once you have handled high availability, the next question comes as to what is your disaster recovery plan? And the disaster recovery is a lot harder to get right than just high availability. And the reason for that is, it actually boils down to your business requirements, right? So the first question you have to ask yourself is, what is the expected behavior, or what is the expected outcome from a business if an entire region is down, right? And in some cases it might be okay. For example, if AWS East goes down, half of the internet is down anyways. So it might be okay, and you can just wait your time until they bring it back up. But if the answer is no, we need to be up all the time, then we need to start thinking about a disaster recovery. And the problem with the disaster recovery plan is that it needs to be a holistic plan. If you just do disaster recovery setup for your databases and don't do it for your application servers, it doesn't really make any sense. So you have to make sure your load balancers are set up correctly, your application servers are set up correctly, and then the database servers as well. So essentially, this just dovetails into your big sort of disaster recovery plan. And in order to get it right, you need at least 3 regions. Again, the goal is, let's say you deploy a 3-node replica set and 1 replica in each region. And essentially, even if an entire region goes down, you still want quorum. Quorum for essentially 2 nodes, and they can basically elect a new master. So if you want to do disaster recovery right, you essentially have to set up 3 regions, and you have to distribute 1 replica in each region. And
what is the difference between a region and a AZ?
So a particular region can have multiple AZs. Okay. So AZ is like some strong guarantees within a region. So for example, in US East, Amazon will give you 3 or 4 AZs. Okay. And then ideally, you can just distribute your replicas within the AZ, and you're fine for 99% of the scenarios, right? But in case of certain businesses, 99% is not good enough. You need 100%, right? So in that case, you might have to go across regions. And a lot of the Amazon services only work in the region. For example, let's say you're using elastic load balancers. They only work in the region. You can't load balance across regions, right? That's why it gets pretty tricky. The technical bar is fairly high to deploy something across regions. So, if you want to do that, you want to make sure your management understands that this is a fairly high bar to deploy. And what we recommend for our customers is, essentially, if you have a VPC deployed in Amazon, pick 3 regions, have 3 VPCs, and set up, VPC peering between the 3 regions, right? And this kind of makes the whole cross-region thing fairly seamless. And it's not ideal in that, for example, security groups don't work across regions. So you have to do all your firewall management with IP subnets, like in the 90s, you have to go back, and essentially everybody has to have their own subnet, and you have to make sure the subnets don't overlap, and you have to do all this. So it's still messy, but it's better than just doing it manually. And some of the other things to keep in mind when you're doing cross-region replica sets is latency. Let's say your main region is US East, and maybe your failover region is US West. Now, if US East goes down and your primary moves to US West, your latency is going to increase fairly dramatically. So from the application side, you need to be, make sure that the business side is required this way. Backups, your traditional, all the traditional ways of backing up your database will continue to work in the cloud. So if you are doing it in a particular way, you can still continue to do that. But the cloud also gives you a lot of new and interesting options. And the simplest option, which a lot of people do, is basically logical backups. Essentially, that's Mongo dump, Mongo restore. And it's very simple. It's just a linear dump of the data, and the amount of time it takes is proportional to the amount of data you have. Right? So it's very simple, and it works very well when you have a small amount of data. But as your data set starts to grow in the hundreds of GBs and terabytes, this model breaks down. And the reason is, if you are dumping out a terabyte of data every day, it's going to take 12 to 13 hours. So while it's a good start, long term is not a good solution. And here the cloud infrastructure gives you a lot of options. For example, if you're on Amazon and you're using elastic block storage, which is the traditional disks in Amazon, and they have the concept of snapshots. So basically, they're point-in-time snapshots, and essentially you can use that to create a point-in-time snapshot of your database. And the added advantage you have is that the snapshots are disk snapshots. So let's say you have a 10 terabyte disk, and you take a snapshot today, and then next time you take a snapshot, it just stores different changes in the disk. So it doesn't need to snapshot 10 terabyte every time. So it's a disk snapshot, and it's also copy on write. So when you're doing a restore, it doesn't need to copy the 10 terabytes. So it will just create the disk, and as and when you try to access that particular block is when it's popping.
So normally in MySQL, when we can use snapshot, what we do is we do a flush, so that all the time in memory goes to disk first. When we take EV snapshot in Mongo, similar thing happens? Or is it like, how do I synchronize my flush with the EBS snapshot?
Yeah, Mongo has a similar command. You can flush it's called flush and lock. Okay. So essentially what you can do is you can flush the contents to disk, right? And then you can tell Mongo don't write to disk, till you trigger the snapshot. You don't need to wait till the snapshot is done. Basically you trigger the snapshot and then you unlock the lock.
If my DB is, let's say, 500 GB in size, how much time will it take for the EBS snapshot complete?
So the EBS snapshot basically depends on how much change has happened in the database. It's a disk snapshot, right? So you don't need to wait for the snapshot to complete.
Once triggered, I can move on.
Once triggered, you can move on. So essentially, it will guarantee that you'll get a snapshot at that point. Right? So for example, if you have a large 10 terabyte volume, it could take if it's a first snapshot, it could take 6 hours, 7 hours, but you don't need to wait. So the interesting point is, flush the contents to disk, trigger the snapshot, and then move on. And the beauty of the actual benefit of snapshots is in restore. Because let's say you want to restore and you want to create a 10 terabyte disk from the snapshot, you don't have to copy 10 terabytes. It's copy on write. So it's just the instant operation. You create the new disk, and it will only copy the data on write. So it's a hugely beneficial feature. And if you want, you can also store some of your backups in S3 if you want more offline backups. And Azure has similar functionality. Whether you have standard disks or if you have premium disks, you can essentially do snapshots of these disks and use them in a very similar fashion.
What are the snapshots?
So think of a disk snapshot as a point-in-time copy of the disk. Okay? So let's say you want to back up every hour, right? So you could essentially take a snapshot every hour. And when you want to go back to that point in time, you can just pick that snapshot and recreate the disk. So if you are familiar with LVM snapshots and things like that, it's very similar, but it's being done on the infrastructure, the hypervisor. Make sense? So performance is like a really big topic. We could probably have 1 or 2 talks just on performance. but I'll do my best to summarize in a few slides. And essentially, MongoDB performs.
Can you go back once? So, Amazon has AWS Snapshots. Azure doesn't have anything like that?
Azure has a similar. Azure basically has standard disks and premium disks.
Okay.
So they also support point-in-time search.
So just the snapshots?
Yeah, this.
Okay. And when they snapshot, do we get charged for it?
So the charge will depend on how much data is there in the snapshot. So let me give you an example. Let's say you have a 10 terabyte disk. Okay, you take a snapshot today, and when you take a snapshot tomorrow, let's say in 24 hours, 1 terabyte has changed. Okay, so what AWS will do is it will copy out those 1 terabytes of blocks, and you'll be charged for 1 terabyte snapshot size.
Okay.
So it won't charge you for the full size every time. It's just for what has changed.
And how long the snapshot will be retained?
It's up to you. You can retain it for as long as you want. Right?
Same as Azure.
Yeah, everything is. Any other questions?
When you say Snapshot stores in S3 already.
So in the backend, it's actually implemented as S3. But if you have your own S3 bucket, in some cases, some customers want to store a copy of the backup in a different medium, right? So they extract the data and they can store in S3 buckets. But that strategy only works when you have small databases. If you're dealing with terabytes, that strategy. Coming back to performance. So performance in Mongo is essentially like it's a RAM and a disk scale, right? The more RAM you have, the more performant it will be. The better disk you have, the better performance it will be. And I think in general that's true about databases in general. And typically, CPU is not an issue. There are some special cases. For example, let's say you're doing a lot of aggregations which have a lot of in-memory sorts. At that point, CPU becomes an issue. But in general, it's not an issue, right? So what we recommend to our customers is, you have different SKUs on various clouds, right? There is the memory optimized SKU, there is the CPU optimized SKU, there is the disk optimized SKU. So our recommendation is to start with the memory optimized SKU first. The memory optimized SKU also tends to be cheaper than the CPU optimized. The CPU optimized SKU is usually the most expensive.
You mean the VM is more optimized towards, when you say SKU, what do you mean over here?
So if you go to AWS or Azure, right, when you pick the different VM types, okay, so you can pick your CPU and disk that comes with the VM, right? Okay? So they are not all equal. Right. So for example, let's say you want to pick something that is doing a lot of processing power, right? So you want a fast CPU.
Okay, got it.
Right? So essentially you pay more for it, right? So for Mongo, you might not want to start there because Mongo typically is not CPU. Right? So what we recommend is pick the memory optimized SKUs, and they cost less because their CPUs are weaker. But in most cases it's okay because you don't need a lot of CPU, right? So for example, the R5 series is the memory optimized series in AWS. So you can start with that, and there if you see that you're being bottlenecked on CPU, then you can pay more and switch to a CPU optimized SKU. And again, similarly in disks, you have a lot of options for disks in Amazon. Right? So the typical disk that comes in Amazon is the EBS storage, the elastic block storage. And there are two variants of EBS standard and EBS premium provision IOPS. So essentially in EBS standard, the IOPS are fixed. You essentially get 3 IOPS per GB of storage. So essentially, if you deploy a 500 gig disk, you get 1,500 IOPS per second. And there is more nuances there as well. For example, if you don't use your IOPS, EBS will essentially bucket your IOPS and let you do a burst up to, I think it's up to 30,000 IOPS. You can, bank it, and when you have a burst of IOPS, you will use it for that burst, right? But it's fixed in that you only get 3 IOPS per GB. So if you want a faster disk, you have to keep deploying bigger and bigger disks, right? And there's also no real SLA for EBS standard. For example, your performance might get impacted by what your neighbors are doing. So if you're looking for an SLA, if you want guaranteed IOPS, and or if you want more control over the IOPS and the disk ratio, you should go with EBS provisioned IOPS. And EBS provisioned IOPS, you can control the size of the volume, you can control the number of IOPS for the volume. So essentially, you have full control over your disk infrastructure, and that control comes at a price. EBS provisioned IOPS are fairly expensive, and a lot of our larger customers they end up paying more for provisioned IOPS than they do for computers, right? Because just to the nature of the setup. And there is a third type of disk in Amazon that's very interesting. It's the local SSD. And just to give context, right? EBS disks are network disks. Think of them as like similar to iSCSI or something like that, but it's a custom protocol from Amazon, and there is no local attached disk. Everything is remote, and they maintain multiple copies of the disk and things like that. And because it's a remote disk, latency is fairly high. If you have a bunch of small writes, you will see it fairly quickly. Right? So the other option that is there in Amazon is local SSD. These are your traditional, NVMe SSDs. They are attached to your local machines. So they offer the lowest latency and best performance of all the disks in AWS. And they are cheapest as well. And it comes with a caveat. So all these disks are ephemeral. So if you ever stop the instance, you lose the disk. Permanently. Okay. So that's why you need to be very careful when you're using these local SSDs.
So even if I stop a VM but don't destroy it, I lose it.
When you stop the VM, the disk is gone. Because the reason is, when next time you start the VM, it might start on some other hypervisor. Okay? So essentially, they don't want you to, develop bad habits and assume that you'll come back on the same server. That's why they don't give you these disks.
Failover also may not be there.
Pardon me?
Failover also may not be
Yeah, if the disk fails, you essentially have lost that.
local.
Yeah, it's a single spindle. So if there is a hardware failure, you lose it. But the flip side is it's very fast and low latency and high throughput. So it's a first-year bargain, right? And essentially, it's a very compelling option. So what we do in ScaleGrid is we offer something called a high-performance key to leverage this local SSD, and we set up a 3-node replica set. And the primary and one of the secondaries will be on local SSD, and the third node will be on EBS, right? So essentially what that helps you with is 2 of the nodes are going at a really fast speed, and the EBS node gives you the safety in case the entire data center goes down, right? So a lot of our customers, especially customers who are doing heavy writes, use the high performance model.
You need to continue to replicate whatever you are maintaining local SSD.
Yeah, the local SSD node will write locally, but there will be a EBS node replica, and that will continue to replicate from the local SSD. And the tricky thing to watch in that model is to make sure that your EBS replica doesn't fall behind by too much, right? It will still have difficulty keeping up because the local SSDs are so fast, but you want to make sure it's bounded and stable.
When it happens to snapshot.
So your snapshots are not supported on local SSD, they're only supported on EBS disks. And that's another reason to always have an EBS copy.
So how does it happen when snapshot?
Pardon me? Can you repeat the question?
So without snapshot, how does it happen? And this is just a delta.
So Mongo has its own built-in replication. So think of it, it's if you are familiar with the traditional, relational like bin log, wall. So it is Mongo has something called the offlog. So it's writing the offlog and it's essentially transferring it to the log. So that is the built-in replication. So you have a lot of options, and there's a lot of trade-offs with every option you choose. But the good news is you have options. So Azure is similar. A lot of these things that we talked about work identical in Azure. They have different SKUs, CPU SKU, memory optimized queue. And our recommendation is typically start with the memory optimized queue and then work your way from that. And there are multiple types of disks in Azure as well. And the default disk is the EBS standard disk. And it's for small databases it's fine, but they have a limit of up to 500 items. That's all you get from the standard disk. So it's fairly limited use. Maybe for dev or test, you can use EBS standard. But if you are starting to go into the standard disks, if you are trying to go into production, you should use premium disks. And premium disks, they come in a variety of sizes, and the IOPS depend on the size. So our recommendation is always use premium disks. And Azure also has local SSDs. The behavior is very similar to AWS. Blazing fast disks, but ephemeral disks. So I think if you're looking for a simple option to start with, on AWS you start with EBS provision IOPS, and on Azure you start with premium disks. And networking, we talked a little bit about networking. It's a complex topic with many layers, but I'm going to distill it in one slide. And essentially, if you are on AWS or Azure, they do have the legacy models where everybody is deployed in a shared LAN, and everybody gets an IP in the same space. And I would highly disrecommend that. You should use the new models that have a software-defined network. On AWS, it's called VPC, Virtual Private Cloud. On Azure, it's called VNET, Virtual Network. So I would highly recommend, if you are using the classic model, just switch over because the benefits are tremendous in the software defined. And in fact, on AWS, a lot of the new types only work if you are on a software defined. So they are not giving you a choice; they are forcing you to move to a VPC. Right? And it has several advantages as well. Essentially, you can set up multiple VPCs. You can bring your own address space. You can set up routing, and if you have an office location, you can set up a VPN connection to your office location as well. So essentially, this is more like the traditional IT control network, and you're probably better off in the long run starting this way. Any questions? We'll talk a bit about security. And I think the fundamental question when you start on the security side is essentially trying to understand who needs access to the DB. It's a very simple question, and essentially you want to grant access only on a need-to basis. So only people who need access to the DB should be able to connect to the DB. And both the clouds provide various firewall functionalities. On AWS, you have security groups. You can use that to control who's going to connect to your database. On Azure, it is something similar. They're called VNET security groups, and essentially you can control access. Basically who can connect to which port of the database. Okay. And another recommendation we would have is, we would recommend you deploy your database in the VPC private subnet. And essentially, private subnet is a subnet that is not directly routable to the internet. So you can deploy it in a private subnet, and your application servers are typically deployed in a public subnet, and only your application servers can reach your database. And the production system usually also have requirements for encryption in transit or encryption at rest, and there you have multiple options for both these requirements. MongoDB has native support for encryption in transit, so you can enable SSL, you can deploy your certs, and especially if you're deploying a cross-region replica set, then you definitely should enable SSL because your data is traveling over untrusted networks. And disk encryption can be enabled as well. Disk encryption at rest, essentially what it means is that your data, when it's stored on the disk, it's stored encrypted. and there are multiple options to do it. You can do it at the OS level, and you can also do it at the cloud level. For example, AWS disks and Azure disks, they support native encryption. So it's just a checkbox on your end and you can enable it.
Would encryption increase latency?
Pardon me?
Wouldn't encryption increase the latency?
Yeah, it's definitely not a free lunch. So there is a performance hit when you do encryption. And typically the performance hit, more than latency, it's mostly a CPU hit. Because what happens is the encryption happens when it's moving to the buffer in RAM. So once it's in RAM, it's always unencrypted, so you don't see that much latency. But you definitely see a CPU hit when it's going between RAM and disk, right? And on a ballpark, on average, we see about, I would say, your CPU will increase by about 30% if you enable encryption. Once you have your databases up and running, the next thing you will hit is scale. Once you start getting a lot of workloads, then you will see that things are getting slow. Now the next option is you want to move up to the next size, right? And in Mongo you have multiple options. You can scale up in place. We call that vertical scaling. Or if you're deployed shards, you can basically scale out, which essentially means you can continue to add shards. And we'll talk a little bit about scale up. And essentially what you're looking to do is you're looking to increase your instance size, you're looking to increase your RAM, maybe you're looking to increase your CPU capacity, and you can all do that in place without any downtime. And essentially let's say you have a master and 2 slaves. We'll start with 1 slave, we'll stop it, change the instance type, bring it back up, wait for it to sync up, then move on to the next node, take it down, and so on. So essentially you can upgrade your entire cluster in a rolling fashion without any downtime. And the only impact your application will see is essentially a failover from one node to another.
Mainly master actually.
Pardon me?
Mainly master.
Yes. Basically when you want to scale the master, you have to step down the master. So once you step it down and before the new node becomes master, your application will see some impact. And typically in Mongo that takes about 20 to 40 seconds.
Okay. One question over here. In MySQL, when you do master switch, it's a manual process. In Redis, it's automated through a container. What's the case in MongoDB?
So Mongo is built in HA. So you don't have to do anything extra. So as soon as you step down the primary, the secondaries will elect a new master.
Can I, even when master is up, can I manually switch over to a different state through a command?
So basically, so just to make sure I understand your question, you have a particular master
And a slave.
and a slave.
I don't want the master down, I want to switch over the master to the slave.
Correct.
Master level. So that there is no downtime at all.
So in a master-slave sort of database, you cannot switch without any downtime. Because essentially what happens is it's a polling mechanism, right? The nodes are constantly talking to each other. And once the master doesn't respond for a certain period of time, the other slaves will elect a new master. So if you are in a single master model, you will always have downtime. But if you want to go with a multi-master model like Cassandra, then you can do without downtime. Right? But that has its own set of problems because there can be consistency issues, right? So this is basically, we are choosing consistency over availability. Right? This is the cap here, right? So as long as you are in this model, you will always have a small amount of downtime. So basically, Google will not run on MongoDB because Google can't be done. But for the rest of us, I think it's okay. And essentially, it's the same mechanism. You can do a rolling job. You can do it on AWS, Azure, any cloud as well. You can change your instance type, bring one node. And the scale out is the unique option for MongoDB sharding. And this is essentially, if you have set up a MongoDB shard and you have set up your schema correctly, ideally you can just keep adding shards as you scale. And Mongo will do the automatic distribution. And you should be able to scale your reads and writes with it. Right? And it works very well. We have a lot of customers doing hundreds of thousands of operations per second. and essentially, think of it as a transparent operation. And let's say you have 2 shards and you decide to add 2 more. There is a process to bring up the replica sets, and adding the shards is instant. But then what happens is once the shards are added, MongoDB in the background will do a rebalance. Right? So what it does is in the background, it will rebalance data from each shard to the other shards as well. And the way the rebalancing works is offline. So it will continue to rebalance, and if during the rebalancing it doesn't get any writes, it will move the data over. But if it gets any writes, it will abandon its stuff. So, but it's an online process. So essentially, you don't have to stop your application. And it's just that it's a slow process. It takes a long time, and you just have to wait till all the shards are redistributed, and then it's any questions on scale out? And another option for scale out is if you have replica sets, you do have the option of adding more replicas. For example, if you are from the MySQL space, it's something like a read replica. Right? Let's say if you want to read from your secondaries, and your application is primarily a read application, then you can continue to add as many replicas as you want, and you can scale your reads down. There's a laundry list of maintenance operations that once you have a production server that you have to pay attention to. Like for example, if you have a lot of inserts and deletes, essentially over a period of time your data files get fragmented. Right? And MongoDB doesn't auto-compact your database, so we recommend maybe a couple of times a year we should do a compact operation. And essentially we can do a compact as a rolling operation as well. We'll take one node out of the replica set, compact it, then bring it back out, wait for it to sync up, and then move on to the next one. So you can do a rolling compact of your database without any downtime.
Compact is like archiving.
I would say compact is basically, it's not archiving, but basically it reduces the internal fragmentation in the data files so that operations get faster.
More like optimize?
It's an optimization. Essentially, your data, instead of being distributed at different parts of the disk, it will all move into a single part of the disk. So your indexes will work better as well. And similarly, we have you should have similar rolling jobs for OS patching as well. When you want to patch the OS, you want it to be a rolling operation. And version updates as well. And Mongo version upgrades are similar to MySQL. Essentially, what you can do is you can upgrade the slave, make sure everything works, and then move on. And once your cluster is up and running, you want to make sure that you have monitoring set up on your database servers. You definitely want to be monitoring your usage. Network usage, and Mongo has a whole bunch of different metrics. You want to make sure you're looking through the write operations, the read operations, the tickets, and there are a whole bunch of monitoring consoles for MongoDB. We have our own custom monitoring console. You want to make sure that once you're in production, you have access to the monitoring console. That way, when there's a problem, you can quickly identify what's going on.
In what language is Mongo written in?
Mongo is written in C. It's a native, yeah. C and C++. And another issue that you're guaranteed to have once your server is in production is, people will say, hey, the server is slow. And it's typically not a server problem, it's a query problem. So you essentially want to find which queries are running most frequently, which queries are scanning the most documents, which queries are returning the most documents, which queries are causing the most blocks. And essentially Mongo gives you several options to log these queries. So you can turn on these logging options. You can log to file, or you can log to a collection as well. When you log to a collection, it's easier to consume, but there is a perfect, because you're actually augmenting your writes. So you can choose different options. We typically choose the option where you write to a log to a file, and we put the file on a different disk, so it's not competing with the data file.
Are there tools available to read and comprehend these files? Like in MySQL, we have performance schema. Similarly, do we have something in MongoDB?
Yeah, so there is a schema that you can write to, but it comes with a risk impact, because if you write to the, they have a slow query table. If you write to that table, then you're increasing the disk load on your system. So that's a tricky part. So we prefer to write to a log file, and we put the log file on a separate disk.
No, my question was, is there a tool to analyze the log file?
There are some tools, some primitive tools, but we have written our own sort of parser.
Okay.
So I'm sure you can. There are a few open source tools you can go in, and you can. And then the format is fairly simple as well. It's similar to the format you see in MySQL. It's JSON here. It's actually simpler to consume, and it's fairly simple to analyze. And typically, like 99% of the time, your problem will be that somebody added a query and didn't add it expert. Like typical, right? So if there is a number called nscan in the query log, you can just look at it. If the nscan number is in a few million, you have your problem. That's it at a high level. So this is some of our learnings and different aspects of deploying and managing MongoDB. And I'll still be around here, so if you have any questions, I'm happy to chat out. Okay? Thanks, folks.